All right, great. Well, welcome. Thank you very much for coming. As we get started, I have a confession to make. I'm bad at maths. I'm like way worse at maths than you might reasonably expect. I did maths all the way up until the end of high school. I did okay. I passed enough to get into university at least. And when I went there to study computer science, I had to do maths again for my first couple semesters. And it turned out the courses were almost identical to what I'd done in high school. So you'd think that, after another year or so of studying this stuff, that I have a better understanding, I'd be able to do better, actually get decent grades. But I feel like I actually did worse. And that's not just to do with harder marking schemes in universities or anything. This is like me sitting in a classroom and just staring at a whiteboard or a blackboard and having no idea what is going on, just having my brain completely freeze up at all of this mathematical notation and just having the worst time. So I am bad at maths. I am interested in maths, though. I'm interested in the areas which inform programming, which help us write better code, which help us write code which is more understandable, testable, which builds upon strong mathematical foundations. So I do want to learn this stuff. I want to learn things like category theory, like set theory, like abstract algebra. And so, I taught myself. But I kept on having the same problem of flashbacks to when I was just staring at a whiteboard and having no idea what was going on, reading Wikipedia articles and just getting nowhere. And I thought that was just me. Recently I saw this tweet. I used to think I wasn't smart enough to understand Wikipedia articles on math and computing, and have recently come to the realization that no, the articles are just badly written. Maybe there are some people that these articles work for. I'm certainly not one of them, and now I know that there are many, many others out there who, have the same problems. So this talk is the talk which I could have used when I was teaching myself some of these concepts. I wanted to have this talk there for me. So this is hopefully my gift to all of you who have the same problem. I'm not aiming for accuracy in this talk. I will be throwing out just a bunch of arrows, a bunch of examples, trying to get you to build up an intuition for the concepts which I'm talking about. So if you want accuracy, maybe look for a different resource. Probably not Wikipedia. All right, before I get started on the meat, I have left quite a lot of time at the end for questions because people often have a lot of questions about these concepts. I will be keeping one eye on the Remo Q&A. So if you have any small clarifying questions you want asked, just drop them in there and I'll do them throughout the talk. But any larger questions, I'll get to the end. All right, let's talk about std accumulate. You might be familiar with accumulate. It's one of the algorithms in C++, which is not in the algorithm header. It's in the numeric header because, C++. But this is what it looks like. Say we have a vector of integers, then we can accumulate them. We can sum them up. We pass it a begin iterator and an end iterator and an initial element, and it will sum up all of the elements in the vector, and we'll get our result. We don't just have to, add them. We could, for example, multiply them. If we pass this multiplies class, then this is going to multiply all the elements together instead of add them. So it's customizable, just like most of the algorithms in the standard library. This is often called a fold, and you can kind of see why if you look at what's going on. If we have this range from 1 to 10, and we take our plus operator, then we're kind of folding it over all of the elements until we get a nice origami crane or something. We don't just have to use integers. We could accumulate lots of different things. We could accumulate strings. Like this will concatenate. This is because I originally gave this talk at CPPCon. So you could say hello CPPCon, you could say hello meeting C++, whatever you want. You could just concatenate strings and this will all work. I haven't had to, say I want to concatenate strings. It's all just worked out because, strings have a plus operator. We could also implement a lot of different algorithms in terms of accumulate. So this is a function which takes in a first and last and a predicate, and it's going to accumulate them all using this this lambda, which just uses logical and after applying a predicate. This is called std all of. It's not quite std all of because std all of will short circuit, but it's essentially the same thing. It will give us the same answer unless you're doing something weird. And we could actually get std none of if we just change the name and we flip the predicate. It's the same thing. It's the same pattern. We're just, changing some of the implementation details. And if we change a few more things, then we can get std any of. The point is that you can actually implement a huge amount of the algorithms in C++ in terms of std accumulate, or at least get some approximation of them. So most of the algorithms in C++ are kind of like this screwdriver. It's useful for a lot of things, but it's still kind of specific. Like this is a flathead screwdriver, so we'll work on flathead screws of a certain size. It's general, but it's also kind of specific to certain areas. Whereas accumulate is even more general than that. It's more like a sonic screwdriver. If you're not familiar with Doctor Who, this is just like, screwdriver taken to its extreme. It can do anything. It's incredible. So accumulate is a more general algorithm which you can implement other algorithms in terms of. And it's so general, we actually invented our own syntax for doing this based on variadic templates. That's called fold expressions. This is a C++ 17 feature. So for example, if you have a variadic template, this is using the C++ 20 abbreviated function templates, but it's the same as you could do this in C++ 17 just by, decorating it with template and things like that. But the idea is we take some number of t's and we're going to fold this plus operator over this pack. And so when we instantiate this template with, say, 1, 2, and 3, then it's going to generate code which looks like this. We have a function which takes a, b, and c, and it will do a plus b plus c plus 0, 0 being the initial element. All right? So it's the same thing. It's an accumulate. It's a fold. It's just some syntactic sugar for it. So let's look a bit more at this call to accumulate. We have a pair of iterators. We have an initial element. And we have a binary operator. Now, of course, we could flip this operator, but then we need to change the initial element because, we're going to multiply some range. If we start with 0, then we're going to end up with 0 at the end, which is not very useful. So we need to change this to a 1. So your initial element is going to depend on what your binary operator is. What you usually want here is what's called the identity element. The identity element is a special element of a set which does not change the other input to a binary operator. Special element of a set does not change the other input to a binary operator. So a bunch of examples, some of which we've seen already. For int and plus, then it's 0, because if you add anything to 0, then you get the thing back. Similarly, for int and multiplication, it's 1. Multiply anything by 1, you get the thing back. String and plus, empty string. You kind of get the picture. Some others, set and union. If you have a set and you union it with an empty set, then you're going to get the original thing back. For bools and logical and, it's true. For bools and logical or, it's false. You get the picture. The idea is that the identity element does not just depend on the data type. It depends on the pair of the data type and the binary operator. So let's look at the binary operator a bit more. Now, say we have this range. We could sum up everything. What if this range was even bigger? If it was something which was large enough, we didn't want to just do this operation on a single core. We want to split it up over multiple cores or multiple machines or whatever. We could distribute this. We could split up our range into and like chunk it up, give different parts of our range to different cores, or different machines. And then, we could sum up everything which is on one machine, and then we could sum up those results, and then we could sum up those results, and we get our final answer. So you can see how this easily parallelizes. But what if we wanted to fold minus over these? Maybe a bit contrived, but this is mostly for illustrative purposes. If we fold this operation over in serial, then eventually we get minus 53. And if we try and do the same thing, we parallelize, we split everything up, then we get a different answer. Instead of minus 53, we get minus 23. That's not great. We would like that if we do something in serial or if we do it in parallel, we should get the same answer, right? So this depends on the associativity of the operator, where associativity means an operator where the grouping of the operands does not matter. Or in slightly more concrete terms, if you have some operator we'll call star, not necessarily multiplication, could be anything. If you do A star B star C, then that should be the same as doing A star B star C. The parentheses shouldn't make a difference. Okay, that's associativity. So the parallelization depends on the operation being associative. And we actually have an algorithm in C++ 17 called std_reduce, which is exactly that. It's a parallel version of std_accumulate, which requires the operator to be associative. It also requires commutativity, but we're mostly concerned with associativity in this talk. So what we have is we have a data type. We have a binary operator, which is associative and which returns the same type as its arguments. And we have an identity element. Now, it turns out that this structure is everywhere, like pervades across the whole of mathematics, the whole of computer science, and it's called a monoid. You might have heard this term, and if you're anything like me, you heard it a lot and had no idea what it meant, even when people explained it to you. But hopefully with some examples, you can see it's not that complicated. Data type, associative operator, identity element. That's a monoid. So if you have types you're composing often, you might be able to expose a monoid. And doing so will allow you to clearly define what object composition means with your binary operator, and then turn those binary functions into n-ary functions, functions which work on any number of inputs, because you can do that full operation. And it also allows you to unlock parallelism because you have associativity. Okay? When you start looking for monoids everywhere, you start to see them in places you might not have expected. Like say we have some large corpus of text and we want to count the words in it. We want to see like how many times a and chicken and whatever are in our text. Then we could have this type word count, which is just a map from strings to longs, and we could have a function which counts the words, which takes in a string and gives you a map of all of the words to how many times they occurred. We might want to parallelize this. We might have a huge corpus of text and we might have a bunch of machines which we want to distribute this computation across. And we can do that as long as, if we're looking for monoids, we're looking for composition. If we can compose these word counts, then we can say to every machine, count words in some chunk of text and then compose them. So we would need a function like map merger or whatever, which just takes a couple of word counts and then composes them into a single word count. If we have these functions, then you could imagine our client code might look something like this. And we have our text, our corpus, then we could chunk it up over some number of machines. this distributed system is something I made up, but you can imagine kind of what it is. It tells you like how many machines you have and has some description of how to run them on different machines. Then we could use std transform reduce, which is essentially does a transform and then a reduce, like a distributed accumulate. And we give it our distributed system. Again, this is something I'm kind of made up. Like in C++ 17, you can give it a execution. You can tell it to do it in parallel or in or sequentially. You can't tell it to run it on a distributed system, but this is something people are working on. Like this is not far-fetched. So we give it our distributed system to run it on. We give it our range of our chunks of text. We say our initial element is an empty map, and our reducer is going to be our map merger, and our transform is going to be count words. So every machine is going to count the words, and then those are going to be reduced using our map merger function. So this is a monoid. Our word counts form a monoid with our map merger function. Again, that pair of data type and binary operator. The data type being the map, the binary operator being our merger. So that forms a monoid. Let's look at the implementation of map merger, or at least one implementation. We could loop over all of the keys and values in the right-hand side. If the left-hand side has that key, then we're going to add the count we got from one machine to the count we got to the other, and otherwise we're just going to place the count we got from the right machine to the map. And you see this is like just reducing both the maps into one and then returning the left-hand side. But we could actually generalize this. Like, we've got this plus operator. Turns out we could actually have this be something completely different. We could have we might not be counting words. We might be merging different maps for some different cause. So we might want to customize this. We could make this a template and say, we're going to default to plus, but you could supply anything here. And then we're going to take a binary operator, default to just std plus. And instead of doing all the computation here, we're going to return a lambda. We're going to return something which is going to be our merging function. And then we just need to flip our plus equals into calling our binary operator and change our word counts to auto, because this could be something different. So here, we had our map type and our map merger function formed a monoid, but our values and this f binary operator also are a monoid. Like we've got kind of monoids inside monoids. They're just everywhere. So again, if you're looking for monoids, you see them in your computations, and you also see them in like deeper down, and you can expose those and generalize your APIs. Another example, say we have some integers and we want to get the max. We can do this with accumulate, saying we give it the range, we have 0 as initial element, and we're just going to return the max of A and B. This is an implementation of std max element. It's the same kind of thing. We implemented it with accumulate because this shows that it forms a monoid. Our data type is the int, and our operation is max. So this is a monoid. But what about the ordering functions itself? Like here we're using just the default like minus ordering, and we're using just getting the max of the integers. But what if we have something like this session type? And this is like a conference session, has a presenter, a title, start time, duration. We might want to order these in different ways depending on how we're presenting our data. We might want to, have a session list which orders by start time. We might want to just order by presenter names and titles. We might want to do this in different ways. We don't necessarily want to bake this into our session type by like having, a less than operator for session, which says, we're always going to be ordering like this. We might want to do this ad hoc, like say, right now I want to order by start time, and right now I want to order by presenter and then title. What can an interface like this look like? Well, say we have this order by function, which takes a member pointer. Then we could do something like, say, give me the max element of the sessions and order by presenter. I don't really care about the implementation of order by here. It's implementable. You can ask me how later if you want. But what about composing these? Like, if I want to order by presenter, then title, how would I do that? Well, I can write a binary operator. I could use operator bar, and this takes two orderings, F1 and F2. And first, we're going to call F1, and then we're going to call F2 if F1 said, these things are equivalent. I don't care. So we're going to return a new ordering, which is the composition. So first we call F1, and if F1 says these things are equivalent, this did weak ordering equivalent is from the spaceship operator, then we're going to return res. And sorry, if F1 says they are not equivalent, then we're going to return what F1 says. And if F1 said they are equivalent, I don't care, then we're going to call F2 and return that. All right, this is a lexicographic composition of these two orderings. So now we have this API. We can say, okay, give me the max element of sessions, order by presenter, and then order by the title. I think this is kind of nice. And it turns out this is a monoid. We can have an identity, which is an ordering which always says things are equivalent. And we can further convince ourselves this is a monoid because, we could write a fold expression, which folds over a bunch of orderings and uses the ordering identity as the identity. Like, monoids are everywhere, and if you look for them, you start thinking about composition more. If you want to learn more about monoids, I'd highly recommend watching Ben Dean's talks. He has a bunch of talks on monoids, is just generally awesome. In fact, here's a slide which I cribbed from him. Monoids are all over statistics. That the word count thing is an example, but here are a bunch of others, like averages, histograms, Gaussian distributions. All of these form monoids, which means they're easily parallelizable. So again, think about your monoids. All right, let's talk about this. Or if you're not familiar with circuit diagrams, maybe you're more familiar with this guy. Yes, this is stood transform. Or maybe let's talk about stood ranges views transform, because we love our nested namespaces in C++20. Say we have some cats, and we want to make the cats cute. We always want cute cats. One way of implementing this is, have a vector of cats, have a vector of cute cats, and then loop over all of the cats, calling make cute on each of them and pushing them into the cute cats. This code works. But maybe a slightly nicer implementation is taking cats, piping it into transform. Transform will call the function you give it, in this instance make cute, on every element of the range we pipe in. And now we have a range of cute cats. And you can kind of read this. You say like cats transform by make cute. It's easy to comprehend. It's not, we don't like raw loops, or at least many people don't. And this is easier to comprehend, I think, and easier to compose. How about optionals? Maybe we have a cat, maybe we don't. So first we're going to check if we have a cat. And if we do have a cat, then we're going to make it cute. But we could do a very similar thing. We could pipe C into transform, make cute. This wouldn't work with stood ranges views transform, but you could implement this. There's different ways, different implementations out there which do exactly this. And it's the same pattern. We have, in one case, an optional, which we're piping to transform. In the other case, we have a vector, we're piping to transform, but it's the same thing. Or maybe we have a future cat. Maybe we're gonna get a cat sometime in the future. Maybe we have to wait for the shelter to get back to us or something. But we know that when we get the cat, we're gonna make it cute. We're gonna give it a little bow on its head or something. I don't know. So we could say get the cat asynchronously, and at some point we're gonna wait. We get impatient, and then we're gonna make the cat cute. But we have to care about when we get the cat. We have to wait on it. We have to care about the context. We have to care about the fact which we're getting the cat in the future. But we don't really want to care about that. We just want to say get the cat and then at some point make it cute. So we could do the same thing. We could take our future cat and we could pipe it into transform. Just say when we eventually get this cat, then make it cute. We're just queuing up operations. And it's the same pattern. These are different types, future, optional, vector, with different meanings, different semantics, but it's the same pattern. So if our accumulate is more like a sonic screwdriver, then transform is more like a drill. We don't care about what's built up. We don't care about the optional part, the future part, or the vector. We just care about drilling through the context and getting at the values which are inside. This is what the signature for transform could look like. You wouldn't actually implement it like this, but this is just for demonstration purposes. We have transform, which takes some temple of t, so stood optional of int, or stood vector of cat, or whatever. And then we have a function from t to some r. And transform is going to return the same template of r. So if we have a optional int and a function of ints to bools, then we're going to end up with an optional bool. We're not changing the optional part, we're just changing the values inside. We're drilling through the context. Some other languages might call transform map or fmap. So what we have is a container of t's and a function which transforms the t's inside the container without changing the container. But again, it's not necessarily a container. Is a future a container of t's? Not really. It's more like a computational context. It's t's alongside the context that we're going to get these later. So we have t's in some computational context and a function which transforms the t's while maintaining the context. See a question, I'm going to answer that one at the end. And it turns out, again, this t's in some computational context function which transforms them is super general. We've seen it in optional, we've seen it in vector, we've seen it in future. There are way more other areas which this pattern pops up in, and it's called a functor. Note, this is not the C++ function object, a class with a call operator. That's not what I'm talking about. This is the definition of functor from Haskell, which is informed by the definition from category theory. Functor is kind of an overloaded term, even OCaml uses it for something completely different, which is a pain, but here we are. Functor. T's is some computational context and something which can drill through and transform the t's. It's not as easy as just this pattern, though. On that note of function objects and functors, I'd recommend checking out Jackie K's blog post on this. It's quite fun. But alongside this pattern of piping something into transform, the functor has to behave in certain ways in order for it to not be surprising. So there are things called the functor laws. I've tried to port these functor laws to C++. It doesn't quite map nicely, but hopefully you'll see what I mean. So say we have some identity function which just takes in an argument and returns the same thing. Then the first functor law is that if you have some functor and you transform it with the identity function, then you get the same functor out at the end. The intuition here is that if you have a vector and you call ID on every element of that vector, then you get the same vector out at the end. All right. Again, like C++, if these interfaces are copying or we have overloaded things, then it's not quite the same. But hopefully you get what I mean. If you don't change anything, then it shouldn't change anything, is what this means. The second functor law is that if we have a functor and we pipe it to transform f and then transform g, that should be the same as piping the functor to transform with some composition of f and g. The intuition here is, if you have a vector and you loop over it twice, once to call f on everything, once to call g on everything, that should be the same as a single loop which calls f and g. Okay? Shouldn't matter how many times you're looping over this vector, it should be the same thing. Okay? So again, this is about maintaining the context, not changing the computational context, just changing the values. Those are the functor laws. So if you have types you're manipulating the structure of just to change the values, you may be able to expose a functor. And that allows you to abstract away the handling of the context, the vector part, or the optional part, the future part, whatever, and write code at the level of your intent. An example, actually, if you look at the standard template library, this is from a presentation in 1994 to the standards committee from Stepanov and Meng Li, who were designing the original standard template library. Iterators were one of the main things which made the STL what it is, the abstraction of pointers. And iterators actually kind of get you a long way to the definition of functors. In fact, most ranges in C++ are functors itself. So, not all ranges, but most ranges have this kind of pattern where you can, transform them. So ask yourself, is this type a range? If I have some type which is, exposing like operator square braces, should I instead be sending out iterators so that I can treat this thing as a range, I can transform it? Does it expose anything which is a range? Do I have like a function called nth child, where instead I should be exposing like a get children range or something, because then I can transform that, or I can not care about the fact that this is a range. I just care about the values. If you think about these things, then this is like a really practical thing in C++ you can do to expose functors in your interfaces. All right, quick look at questions. Question is, wasn't the first element of each subgroup positive but had to be negative in the parallel minus example? Maybe that's not the important part here. The important part about the parallel minus example is just that things have to be associative. Don't care too much about parallelizing subtraction over a bunch of elements. It's not very interesting. Okay, let's talk about std ranges, views, join. More namespaces. So if I have a cat pic, I might want to do a bunch of transformations to make the cat look cuter. Maybe I want to make the cat smaller. Maybe I want to make its eyes sparkle. Maybe one of these operations could fail. Like if the cat has its back turned to the camera or something, or has its eyes shut, then you can't really make its eyes sparkle. So the second function is going to return an optional cat pic. We might not be able to make its eyes sparkle. So if we maybe have some cat, then I imagine we could do something like transform to make its eye sparkle and then transform to make it smaller. But the problem here is that, make eye sparkle might fail. It's returning an optional, so we actually would have an optional cat pic. So this wouldn't compile, it would just blow up. What we would need to do is essentially strip away one level of that optionalness, which we could do with a join. Join takes a range of ranges and collapses it down into a single range. So if you had a vector of vectors, then it would just make it into one linear vector. If you have an optional of optionals, then you would just have an optional. All right. But then, if we have other functions like add top hat, and maybe that could fail as well, maybe the cat has its hand on its head or something, then we're going to see this pattern a lot. We're going to transform, join, transform, join, transform. It's kind of noisy. And this pattern turns up a lot. So maybe we could invent a function which does a transform and then a join. We could call it something like and then. Other languages might call this bind. So we just say baby cat and then make its eye sparkle and then add a top hat and then transform it to make it small. This is what the code would look like if you didn't do this. We check if we have a cat and then we make its eye sparkle and we check if that failed and then we add a top hat and we check if that failed. And then again, we're handling context when we want to be handling values. We want to care about the data flowing through these function calls rather than caring about like unwrapping stuff and then rewrapping it and unwrapping it and rewrapping it. We want to care about values, not context. Another example which follows the same pattern is futures again. Say we want to pat the cat's head and we want to scratch its belly. At least, I have 3 cats. They like head pats to last a long time and belly scratches to last a long time. So maybe you want to queue up a bunch of operations. You want to pat its head and then you want to scratch its belly. But you don't want to care about when these operations finish. So say we have a good boy and we want to pat its head and then scratch its belly. Again, we're caring about the values, we're caring about the data types flowing through these function calls, not caring about when the head patting finishes and when the belly scratching starts. We're just queuing up operations. Another example is parsers. You might have seen this definition of parsers. A parser for things is a function from strings to lists of pairs of things in strings. This might not immediately seem like a definition of a parser, especially in the C++ world. We're used to more imperatively styled implementations of parsers. But this is how you can implement parsers in pure functional languages. A kind of translation to C++, say we want to generate a parser which matches a character. And we're going to return a lambda, which is going to take some input. And then we're going to have a result. The result is our list of pairs of things and strings. You probably wouldn't actually use a std list here and things like that. It's just so that it matches up nicely with the definition. And the result is going to be all of the ways in which you could parse the character C from the input, which is always going to be 1. But there are other situations where your parser could parse multiple different ways. So you want to be able to say, here are all the different ways you could parse this thing. But for a character, it's just going to be 1. So you just check if the input's empty, and you check if the input, if the first character does match your C, and if it doesn't, then you're just going to return the empty result. You can't parse this. Otherwise, we're going to push that pair of the character and everything we did not parse to our result, and we're going to return it. So we're returning the thing we did parse and everything we did not parse. And so this is kind of like not very useful. It can parse a single character, but the useful part comes in when you compose these things. Right now we can just say we have some input, we can match H, and then we can get the front of it to check that our character we parsed is H and that everything else is LO. But when we compose these things, we could do something like this. This is just a small example to show you how it might work. But you could match one of T and F. This is if we're wanting to match like true or false. So match T or F, and then check if we got T, and then match ru, otherwise match alse. We're composing parsers here. In fact, Ben Dean and Jason Turner had an entire talk where they did exactly this for writing a JSON parser, which works at compile time. It's using exactly these concepts. In fact, here's an example I cribbed from them. I just changed it a little bit. It's an integer parser. So first we parse one of 1 to 9, and then we parse 0 to 9, and we build up an integer representation as we go along. This is composing parsers. It's kind of cool. And entire languages are built on this. If you write a parser in Haskell, then you might use exactly these kinds of things. It's a question of how efficient is the functional style code comparing to the traditional procedural approach? It depends. It's the easy answer. Like the benefit of the functional style for a lot of this is reasonability, and in functional programming we often don't have mutable state, so it's easier to parallelize things. It's easier to reason about when changes are going to be made to your system. Of course, because C++ is often built on mutating things, some aspects of the efficiency do not translate nicely to that. There are ways to deal with this. If you look at some of the talks by Phil Nash or Juan Bolivar, they both have talks on immutable data structures in C++ and how to make this efficient while doing like functional style programming in C++. There are ways to get both efficiency and functional style. All right, so if transform is more like a drill, drilling through the context, then and then is more like a pipe with some duct tape. If we have some functions which don't quite match up, we've got some context we need to handle, we're just going to duct tape them together and care about the values which are flowing through these functions rather than caring about the context which is built on top. So we have some t's in a computational context, and we have a function which composes operations which produce that context. Composes things which return optionals or return multiple vectors or return futures. And this is called a monad. I would like to congratulate myself. This is one of the very few talks in C++ which mention monads where I do not make any of the obvious jokes about monads. So I'm very, very pleased about that. Now, there are, of course, monad laws, like with the functor laws. I did the same thing. I translated them to C++, and I had a bunch of slides when I explained them all, and it was all really, really boring and didn't really add anything to the talk, so I got rid of it all. If you'd like to know about monad laws, you can come talk to me afterwards, or you can go look at some other resource like not Wikipedia. But essentially, it's the same kind of thing. Here's how your monad needs to behave in order to be reasonable, so that operations will compose nicely in a way which is not surprising. So if you are manually marshalling data in and out of context to manipulate them, then you may be able to expose a monad. And doing so, again, will allow you to abstract away that context. You're not having to do all the unwrapping yourself and write code at the level of intent. Now, examples of monads, again, like I said with monoids, if you look for monoids everywhere, they turn up. If you look for monads, they turn up where you might not expect as well. Coroutines is an example. Here's some code I stole from Gornishinov. This is a TCP reader function, which, we have a buffer, we open some TCP connection, and then we're going to read a set number of bytes from this TCP connection over and over and over again until we're done. Now, this is a synchronous function. Opening a TCP socket might take some time. Reading from a TCP socket might block, it might take some time. We might want to do other things whilst we're waiting for the connection or for the read over the network. So we could transform this into asynchronous code. Don't try and read this. I don't want you to read this. My only point is that it's horrible. Like, I do not want to write this code. I hope you do not want to write this code. I don't know anyone who wants to write this code. And this is even using, this uses like .then, which is pretty much like and then. So this is using some of the concepts I've already talked about. It doesn't happen to map nicely to this exact example. We're having to create some state, we're having to dynamically allocate it, and then we're just turning all our control flow inside out, and it's horrible. What if we could take our synchronous version and we could get something which is the same as the asynchronous version just by decorating it? We want to wait for our TCP. We want to do something else while we're waiting for our connection. We want to do something else while we're waiting for our reads. And coroutines give us that. We decorate it with co-await, and now we can do something else while we're waiting for our connection or waiting for our read. We also need to change the return type, because we're not returning in 6040 anymore. We're returning some coroutine type, like a task or some future. All right. Note that we've decorated our synchronous code because we do not want to handle the context of the asynchronous calls. We want to focus on the values. We want to focus on the normal control flow. We don't want to focus on the context. Coroutines are a way of exploiting the monadic nature of asynchronous programming, which is kind of cool. In fact, here's some code I stole from Toby Alsop. You can actually use coroutines for optionals as well. So we have a bunch of functions which return optionals or return null ops, whatever. We could have a function which calls F1 and F2 and F3, and we could use coawait to say, if any of these returns an empty optional, then just back out of this coroutine. Don't try and execute anymore. And this actually works. I wouldn't necessarily recommend doing this, but this is just a show that coroutines are exploiting monadic styles of these constructs. It might look kind of like do notation in Haskell, if you're familiar with that. Do notation is a way of making code look like it's straight line, but actually the compiler transforms it into a bunch of lambdas and calls to and then or bind in Haskell. And this is kind of halfway to do notation. It doesn't quite get all the way there, because do notation, sometimes you might need to run parts of your function multiple times. You can't do that with coroutines, because although it does split your coroutine into different functions, essentially, it does not give you a way to get those partial functions out, so you can't execute something multiple times. So it's part of the way to do notation. It's not quite there. But it's kind of interesting, I think. Another is static exceptions or herbceptions. This is a proposal from Herb Sutter, which tries to fix exceptions in C++. I think it's great personally, but here's an example from the paper. So if we have a convert function, which takes a string and converts it to an int, but maybe the string is empty, maybe there's something which is not an integer there, so it could fail. And then we have a function which calls convert and then multiplies it by something. We have this throws keyword. This is not a dynamic exception specifier, which you might be familiar with and should never use. This is something quite different. What throws means here is, actually, I'm not a function which returns an int. I'm a function which returns either an int or some statically known error type. You could think it as like a union of int and some error type, or std variant of int error type, or std expected or result, if you're familiar with Rust. So that's what this is saying. Not a function returning an int. I return a union of int and error. And similarly, these throw keywords inside the function do not mean dynamically allocate this, throw it up the stack, unwind everything, look for catch handlers. No, this means return the error type. Return my union of int and error engaged to the error state, and have it engaged to error empty string or illegal char. So this is not like dynamically throwing exceptions. This is just returning things from functions, but dressed up a little bit. And then when we call convert and stir multiply, if we got the error state from convert, then we're going to automatically return that back from this function. We're not like throwing it up the stack, we're just returning it. So this, again, we're focusing on just the normal control flow, the normal values flowing through this, rather than focusing on the handling of the error context and like unwrapping these unions and things like that. So static exceptions are a way of exploiting the monadic nature of error handling. Again, like monads show up everywhere where you're looking for them. Like we could convert this into something using like a std expected type, just by switching our our return type to an expected event and error, and then returning an unexpected. So here I'm just converting the static exceptions to like normal C++ you could write today. And then the only like real change we need to make is marshalling this context. We need to like convert, and then we want to transform that with our multiplication. One question is, isn't static exception pretty much the same as outcome, just different syntax? Yes, that's exactly what I just showed here. Yeah, it's syntax, but it's also like if it's baked into the compiler, then you can do things like use registers for returning the error state and things like that. You know, because the compiler knows how all of these things work, it can optimize a bit better than if all of this is baked into a library. Yeah, but outcome is a different way of spelling expected here. It's a very similar thing. Yeah, so you can see here, this is the difference. We just switched our error types, the return types, and we had to do some additional marshalling of that convert. So what we have monoids, which are a data type with a binary operator, which is associative, and an identity element. We have functors, which are t's in some computational context, which we can drill through to change the values while maintaining the context. And we have monads, which are t's in some computational context, and we can chain the operations together without focusing on the context. So look for monads, monoids, functors, and monads in your code. And when you do so, you can expose them in your API to allow the clear expression of composition and writing code at the level of intent. Thank you very much. I will have a look at the questions now. So there's one question: where and how will such bubbling up error be handled? Do I need a specific try catch? This is here. I can't remember exactly what the syntax for actually handling these is. I think it's you have a catch, but it's a statically known error type. It's not like this could be anything, which has to be dynamically allocated. How to debug and step through the functional style code effectively? That's a good question. Yeah, so one of the things about this kind of style is, especially if you're doing like asynchronous programming with futures and things like that, then you end up inside like nested lambdas, or the control flow looks kind of weird. So it's a skill. The thing I will say is that it's if you have all of these operations which are being just chained up, then since you're not dealing with context, it's harder to make mistakes. But yeah, when you do have to debug and step through this stuff, then it becomes a little bit more difficult, because you might get your code is going to be called back by some library at some point, and you might know when that point is, but you might not, depending on what your data types are. So yeah, I'd say that doing this kind of thing can make it easier to. It can make it more difficult to make mistakes, but resolving those mistakes and debugging can be a bit of a challenge sometimes. Question is how to deal with the collision of the global namespace with the operator bar. You could do that with concepts, or like screwing around with argument dependent lookup, things like that. There are ways to deal with that. Can you maybe walk through the definition of a ranges pipeline? Looks a bit like bash pipelines, only the initial cat is missing. Is there some laziness involved? So ranges views, which is, like the where's my transform? Right back here. So if I have like a vector and I pipe that into transform, yes, there's laziness in this example. So what happens is when I say vector pipe to transform f pipe to transform g, I get some view out at the end, which represents my computation. And then when I ask for a value, by like looping over it, using the iterators, or like giving it to some algorithm which does not execute lazily, then it's going to call f and g on the elements of the vector. It's not going to do it ahead of time, which does mean that you can represent like infinite computations here, because as long as you don't ask for infinite computations, then they're not going to happen. It's all done lazily. For ranges, generally you have views which happen lazily, and you have actions which happen right now. In terms of like the optional version, where do I have an optional one? Here. This is going to be, you could implement this in different ways. Like, so I have an implementation of std optional which has a transform, and that's done immediately. That's not lazy. But you could make it lazy if you wanted. Any other questions? Still got about 4 minutes left, so time for some more questions in Q&A if anyone has some. Oh, can you recommend books about functional style C++? Yes, I would recommend Ivan Kucik's book. I think it's just called Functional Programming in C++ or something like that. I can't remember the name, but if you look up, like if you Google functional programming in C++, then you'll probably find it. It's good. His talks are very, very good. So yeah, I'd recommend reading that book and watching his talks. Since ranges are now available with this style, are you aware of any plans for future/optional to add similar things to the standard library? So future, I can't remember where future ended up with .then. Like I think we got .then for future, right? But it's not as fully featured as it might necessarily be. And I think the implementation of .then for future is doesn't map exactly to what I talked about with functors and monads, since I think it unwraps automatically. But yeah, future is definitely there for having this style available. Optional, hopefully C++ 23. I have a paper which adds the transform and then and or else to std optional. You could also use my TL optional implementation, which has all of those. Can you share a link to the Stepanov paper? I thought it was lost. I can't remember where I got that slide from. I think I just Googled for Stepanov STL presentation or something and found an image and used that. So sorry, I don't have a link to the Stepanov paper. Any last questions before I wrap up? All right, I think I will call it there. Thank you very much, everyone. Enjoy the rest of the conference.